Hello and welcome to this session on logic gates, logic circuits and also solving problems with logic gates and logic circuits. This is part of the IGCSE Computer Science syllabus of videos and this is topic number 10 for the 2023 Computer Science syllabus. Now what we are going to be doing in today's video is we are going to be exploring logically. So you can see I've just inserted some gates in here which I am going to delete. This is browser based, so if you go to this URL you should be able to use the demo version of the software. And we are going to first start today by exploring the different gates that you need to be aware of for the IGCSE Computer Science series and also syllabus of videos and also courseware. So first of all, if you're a physics student, these should be coming up in physics as well. So the first thing that we need to be able to do is identify the different gates. And this basic logic gates truth table, which has been taken from a source online, this displays all of our different gates. So we've got AND, OR, XOR, NOT, NAND, and we've got NOR. We don't actually need to be aware of this one at the bottom here, but I've added it in for reference anyway. So we are going to start by looking at the gate and understanding the different inputs. So first of all, gate name, and then this is what our gate looks like. This is the schematic. You must be able to label and also draw the gate at IGCSE. Notice that all of our gates going down, they have two inputs, A and B, except for our NOT gate, which only has a single input, and as with the other gates, it only has a single output as well. In column number 3 here, we've got our boolean expression, and this is what we need to do, or how we need to represent the gate in boolean expressions, but also in logic notation at IGCSE, and I'll show you the logic notation in a moment. And over here we have got our truth table. So if we have binary values, so you can treat these as high and low voltage. So low voltage is 0, high voltage is 1. If we have 0, 0 going into our AND gate, we are going to be getting a low voltage output. So what we're going to do is just snip this, and we are just going to take this over to the second page in our Google Doc below. Now, if you don't have access to this Google Doc, or you're not one of my students, obviously do drop me a message and I will give this to you. So first of all, let's take this into Google Drawings just so we can very, very quickly complete the gate. So let's paste this. So what we have to do is we need to identify what the output is going to be for our different gates here. So I'm going to do a squiggly line. So if we have 0 and 0 going into an AND gate, we need both of the inputs to be high voltage in order for the output to be 1. So the answer to this is going to be 0, because both inputs are 0, 0 and 1, so low voltage and high voltage is also going to be 0. If we go to 1, 0 again, only one of the inputs is high voltage, so our output is going to be low voltage, which means 0. And then we are going to have an output of 1 for our gate here. So let me just draw that again so it's nice and clear. High voltage, or 1, 1, gives us an output of 1 for an AND gate. Now with our OR gate, we can have a combination of either A or B can be 1 and 0, or 0 and 1, and also 1 and 1. And in this scenario, we are going to have every single output, except for 0, 0, as 1. So we only need one of the inputs to be 1 to get a high voltage output. So this is pretty much everything that you need to know for the different gates. And what you should be doing in class and also in the syllabus is using your book and the information which is provided by your teacher to identify the correct truth tables for each of the gates. Now we can see we've got a representation of the gate in a Boolean expression, or I would say Boolean algebra, but we also have to write this in logic notation as well for the computer science syllabus. So I'm going to write logic notation underneath, and for AND it would be Y is equal to A and B. So this is what it would look like in logic notation for our AND gate. If we were to write the logic notation for our OR gate, okay, so logic notation, and Y is equal to A or B. And this here is our OR gate. So again, we need to be able to write it in boolean algebra, but also in logic notation as well. Now, you can see the different symbols which we have in this table here. So this is going to be AND, this represents OR, and our exclusive OR gate is the only one with this very funny circle here. We've also got it on the XNOR gate at the bottom as well. So exclusive OR, we can see here, this is the only one with this output here. And what we should probably do at this point is just check what would the output of this gate look like. So let's do XOR truth table, and then this will give us a better understanding of what our gate should be doing. So if we go on to this symbol here, and XOR, we can see 0, 0, 0, 1, 1, 0, and 1, 1. So our only high voltages are going to be when the exclusive OR 0, 1, and 1 or 0 is on. So we use that symbol, which you can see in the previous image, to represent is A or B, okay? It's not going to be 0, 0 low voltage and 1, 1 high voltage. So hopefully that makes sense. And now we can move on to the next part of the session. For the next part of this video, what we are going to be doing is we are going to be drawing a random circuit inside logically, so you can see how you can simulate the circuit and how this can help you to create truth tables for really, really complicated logic gate problems. So we'll use some nice easy gates to begin with. So we are going to use an AND gate, a NOT gate, and also an OR gate. So first of all, to get this working, we are going to insert a light bulb, and we are going to connect it to the final output. We then need to join our other outputs from the NOT gate and AND gate to the OR gate up here. And then we are going to have to add some toggles up here. And these toggles are going to allow us to turn the voltages on and also off. Now, for me, for those students which have trouble tracing problems, this is probably the better way to study logic gates, logic circuits, and also solving problems, because it's going to allow you to trace these different inputs. So white line means no power, blue line means we have got power, and we can see that our OR gate is on up here. Now, on the left-hand side, we should look for our text box button. If I right-click, hopefully we'll be able to see that somewhere. I'm not seeing it at the moment, and here we go, we've got label. So we are going to label our inputs now. So we have got input A, we have got input B, and then we have got input C here. So most important thing, label your inputs. Now, we have got multiple gates here, which is forming a logic circuit, and this means we're going to have an intermediary output, or we can say input. So we're going to label this one here as D, because that's going to decide what combination of zeros and ones is passed into our OR gate. And also over here, we are going to label this one here as E. Now that we have done this, we can label our final output up here. We could call it X or Y, it doesn't really matter. And then what we are going to do in our Google Doc is we will snip this, and then we are going to take this over to our Google Doc, and we are going to have a look at how we would be able to draw this in the form of a truth table. So we're going to paste in the circuit, and we'll go to a new page just so it's nice and easy, and hopefully it's visible for everybody in this video. And we are going to insert a table. So first of all, the table should have the same number of columns as it does inputs, intermediary inputs, and outputs. So that's 1, 2, 3, 4, 5, and 6. So we should have a table with 6 different columns, and we can label these as A, B, C, D, E, and then we're going to have X. And we need to identify the possible combinations of 0, 0, 0, 0, 0, 1, firstly for our inputs here. So first of all, inputs, we've got 0, 0, 0, then we'll have 0, 0, 1, then we are going to have 0, 1, 1, and then we can have 1, 1, 1, and still we've got more combinations of binaries, so we can have 1, 1, 0, and we can have 1, 0, 1. Okay, so far 1, 2, 3, 4, 5, 6, and then we should have 2 more. It should be a total of 8 inputs. So what are we missing here? So we have got 0, 1, 1, we have got 1, 1, 0, 1, 0, 1, and we should also have a few more here as well. So 1, 1, 1 we have. So I will probably leave this with you to identify the missing outputs, or I can come back to this in a minute once I have had my morning coffee. So how do we trace the intermediary inputs here? So first of all, with 0, 0, 0, at this point you should have been able to identify the truth tables for each of your logic circuits. So if I click on A here, that would mean we've got a high voltage one going in. The first row which we are filling out is 0, 0, 0, and input A is 0. So with a NOT gate, when we have 0 going in, we can see that our output for D is going to be high voltage, so we can set this to 1. When we have got 0, 0 going into an AND gate, we can see the output, there is no blue line, that means low voltage, so this is going to be a 0. And when we have a 1 and a 0 going into an OR gate, this is going to give us a high voltage output, so this will be 1. When we move on to our next one here, we're going to have 0, 0, 1. We know that with an AND gate, 0, 1 going in is still going to be low voltage being output, so even if we turn this to on here, in our circuit, there will be no blue line. So what I'm going to do is I'm going to move down into the table where we do have 0, 1, 1. And this should be where our AND gate has that blue line here. So 0, 0, and also 1 up here, or let's reword that, we've got 0 and then 1, 1 going in here. So we've got blue line, and we've got high voltage for output E. So that means with this combination of zeros and ones going in, we've got 1, 1, and with an OR gate we can have 0, 1, 1, 0, or 1, 1, and that's still going to be a high voltage output. So hopefully at this point you are able to see how we can draw a truth table or create a truth table for a logic circuit which has been given to us at IGCSE. And the next thing we are going to have a look at is how we can write this in boolean algebra. Now what you'll be able to see is we have got a complete truth table for the circuit which we have drawn above at the top here. And we've also got a representation of this in a logic notation as well. So the logic notation would be x is equal to not A or B and C for the above circuit which we drew. Now, the next thing that we are going to do here is we are going to have a look at how would we be able to draw a circuit from a logic notation statement that we have been given at IGCSE. So we have got x is equal to A and B, or A and not C. So where would we get started with this circuit at IGCSE? So first of all, over here inside logically, I am going to delete the previous circuit that I had, and I'm going to firstly start by inserting the different gates which we have been given in this statement. So we've got 1 and, 1 or, 1 and 1 not. So for me, this is normally the most logical way to start drawing the circuit. So I'm going to drag on an OR, I'm going to drag on an AND, another and also a NOT gate. And these are all of the gates which have been mentioned inside this logic notation statement. So the next thing to do is establish where our inputs should be. So first of all, we've got A and B. So these are our first two inputs. So we can move our first AND gate up here, and we can move our OR gate to the end. The reason why I'm moving it to the end is because we have got our OR gate in between both of these different statements at the moment, which means that this is going to be our final gate. Back over here in logically, now that we have identified our final gate and input A and B, we can now have a look at the next part of a statement. And that here is A and not C. that basically means there is going to be a shared input from input A connecting to our other gate down here at input C. And that means there will be a shared input. So what is this going to actually look like? So first of all, let's label our different inputs. So this here is going to be A. We will also have B. We will have C. And let's also put the intermediary input, so that's A and B very close together. This is C. And then we are going to have an intermediary output for this one here. So this will become D. And then over here, this here is going to become E. And then we have got X at the end. Now, first of all, let's join the gates. So A connects to this OR gate. We have got not A here, so this is going to connect to the bottom input of this gate here. We said we have got a shared input with input A, which means that this is going to connect to A up here. We have got B connecting here right now, okay, which is good. So we're going to have to add our toggle switches, so light bulb at the end, and also look for our toggles. So here we have got A, toggle switch B, and toggle switch C. A little bit messy, but hopefully this is clear. And now we need that shared input for A. So over here with A, we also want it to connect to this gate up here. Okay, so haven't done this in logically before, so fingers crossed this will be able to work, but we can see at the moment this is not actually working, so let's do this. And there we go. So have had my morning coffee, but haven't used logically for a while, so this is how we are creating our shared input. So at the moment, if we go back to our logic notation statement, we've got A and B. So this is the first part of our problem and our first two inputs here. The next part of the problem is OR, which is our final gate, which is connecting to our light bulb. And then we've got A and not C. So A connecting to the and not C connecting to the second part of the AND. Now, if we look at how we would create this truth table and how would we be actually able to see if the circuit we have drawn matches the logic notation statement. So we've got A and B on. So A and B on. And we've got next part, which is going to be A, which is on, and not C. So with not C at the moment, this means that we're assuming that this is going to be 0. So we haven't turned the input on, which means that our light bulb is going to be high voltage. And this is how we would draw a logic circuit from either a boolean algebra statement or also a logic notation statement. Now, in the next video, what we are going to be doing is we are going to be having a look at a more complex IGCSE problem, and we will be having a look at how we can model a scenario on a factory or a water tank for the IGCSE Computer Science syllabus.